You're listening to Within Tolerance, a podcast for machinists by a machinist. I'm your host, Dylan Jackson from Proteum Machining, and this week I'm joined by Cyrus Lloyd. Welcome, Cyrus.
Thanks for having me, Dylan.
So, for anybody who doesn't follow you on Instagram or know you, hasn't seen your YouTube channel, where can they find you? What do you do? Who are you? All that good stuff.
Yeah, so I'm Cyrus. I go by the internet moniker of Silo's Garage. That's what my YouTube and Instagram are. I'm a student at Auburn University, so unlike a lot of the guests, I don't have a small machining business or anything, but I do a lot of cool stuff in the shop that I work in on campus, just personal projects and work projects too, and I pretty much post the cool stuff I do on those places. The My main job is the technical title is senior Makerspace assistant at the Makerspace that we have on campus. Um, we've got a bunch of neat facility there, but my particular job is running the machine shop. So me and another coworker, Nick, um, we supervise the use of the machine shop, run trainings for everyone, do some, not contract work, but do some machining for other departments and researchers and whatnot. But yeah, that's the short of it.
Awesome. And you've also had a pretty amazing internship this summer, right?
Yes, yeah. So that's where I'm at currently is Minneapolis, working at Professional Instruments for the summer. Um, for those that are familiar with it, you can sort of figure out why that's special. But for those that aren't, I suppose I can explain the backstory behind Professional Instruments a little bit. They're, to summarize very quickly, a ultra precision air bearing manufacturer, if in the broadest terms. They make air bearing spindles, but they also do a lot of custom engineering work, air bearing slides, all sorts of air bearings, really. I think we'll dive into that a little bit later, but that's what a lot of the interest recently, regarding my activities has been on, is like people find out that I'm at Professional Instruments and they want to know lots of things because there's a lot of really cool stuff going on there. Um,
For those who aren't familiar with it, when you're talking ultra precision, what's like a usual tolerance that you're seeing on prints there?
well, there's been some funny prints that I've seen go by, like tolerances on holes, plus or minus 10 millionths of an inch, which not something you're going to see in regular machine shops. I mean, flatness tolerances on large parts less than 20 millionths. Um, the Similar for parallelism, squareness, like basically it's people speak in micro inches. It's a different world, like a completely different level than like your average machine shop. Like Dave, the owner or the vice president, um, basically, like I said, speaks in micro inches. If he's talking about tenths or something, like there's a tolerance of 2/10, he'll say 200 micro inches because that's just the realm that his mind is in. It's wild.
That's super cool. And I imagine, for the rest of your career, everything is just going to be that much easier. When you're used to working in micro inches, you're like, oh, a couple tenths. Yeah, I can hold that.
Oh yeah, I mean the grinders there and the tools we use. If you see like plus or minus a tenth on something, you're like, oh dude, what is this like? a like a welding job or something. This is the lowest tolerance I've ever seen.
Well, and like I think you posted on Instagram the other day that like they were drilling somewhere relatively far away and you guys had to stop work because you were seeing fluctuation.
Oh yeah, yeah. I put that in the Discord. There's a construction site nearby, and we think it was drilling. I don't know what they were doing, honestly. Maybe it was too high frequency to be pile driving, but there was just this massive like shaking that shook the whole building from this construction. And I say massive. It was visible in the windows, and like if you set up an indicator on something, you'd see the needle like shaking around. And yeah, all the finish grinding and the high precision stuff that was going on, they just put a pause on it because it shows up in there. The parts I was running at the time, luckily, weren't of a tolerance where it was really going to affect anything. You saw it in the surface finish, that was for sure. It turned out fine dimensionally though. But yeah, for that high precision work, even stuff like that, it's completely out of your control. They just had to like, nope, we cannot do any work or these parts will not come out to spec, which is
That's
wild.
so crazy. Yeah. Well, I really want to get into more of what you've learned there, but first let's step back. How did you get into machining? How did you get to the point where you're working there, and all your jobs and stuff? Let's step it back.
All right. Yeah. So, I mean, I'm one of those, you know, mechanically minded people who just been like tinkering and building stuff, their whole life basically. Um, and I sort of look at my machining journey and just really building stuff journey as like that, a journey. It's like some people say like, well, and then I got into machining and here's how I started machining and I started and now that's what I do. But I think of it more of like a continual progression. So, you start when you're a kid, you got your duct tape and your zip ties and your hot glue and stuff, and you're throwing stuff together. And then maybe you want to make some cooler things, so you get into woodworking a little, and now you can put things together with screws, and that's neat. You can make bigger and stronger stuff, and maybe stuff with a little tighter tolerances. And then a lot of people that maybe they find welding, and then they can stick metal together, and that's wow, that's just an amazing ability to have. And maybe that's where some people plateau. But I kept wanting to make cooler and tighter tolerance things. So you learn how to weld, and then you have your go-kart phase or whatever. You weld together some vehicles made out of lawnmowers and crap. But
Right. Death machines that you look back on and you're like, how did I survive?
absolutely, absolutely. Um, but where I really started to take that next step into machining was in high school. Um, I am a aerospace major for context, so that is to say I've always been into space and rockets and all that stuff. Um, and early in high school, I got involved with a student run aerospace startup thingy called Atlas Rocketry, where the idea was, it's a bunch of high school kids who like rockets, and we're going to build a big rocket, and, we want to get to space and all this stuff. Pretty ambitious. But they reached out to a local makerspace I was a part of at the time, basically asking, hey, we're this team of these kids trying to build this thing, and we need someone who can help us make the nozzle for this rocket we're designing. And at that point in time, I had no machining experience at all. I was aware of it because I was watching YouTube and I'm like, oh, there's this cool channel called This Old Tony. What's this about? And I was definitely there was some interest. The spark was there, right? I was I was definitely exploring that, but I had nothing. I had a drill press. That was the extent of my machine tool collection. But I also looked into these guys that reached out to the email chain for the makerspace. And I was like, oh, this would be really cool. I was thinking of buying a lathe anyways. If I bought a lathe, I could like help them make this. And that summer, I had been working at a fast food place, making a couple bucks and browsing Craigslist. And end of the summer, I found a 1943 10-inch Craftsman lathe on Craigslist for probably too much money. I think it was like $700, but it was the ones with the extended bed. It can do like 40 inches between centers, which is pretty impressive for the lathe that size.
Jeez. Yeah.
Um, but I bought it. I reached out to this dude. I got myself a little lathe. Got a chuck on eBay because it didn't come with one. Got scammed at first. Bought a chuck that showed up, and it was a independent 3-jaw chuck, which I didn't know existed at the time. But
I didn't either. I just found out they existed.
Yeah, I don't know whose idea that was, but it was not a super handy thing. Anyways, I bought a chuck and responded to these dudes and was like, "Hey, I got a lathe. I don't know how to machine, but your gig seems pretty cool. I would love to, you know, like work together. Maybe we can do some stuff." And they're like, "Neat. That's all we need, basically." So I joined this rocket startup, um, became their manufacturing guy, which I wasn't qualified to do, obviously. But then again, neither was anyone else. Like it was just complete, like, you know, not like zero expertise. No one knows what they're doing. It was a mess, but it was really fun. So after messing around with a lathe for maybe a month or so, my first like real project was, well, we need this 304 stainless rocket nozzle for this solid rocket motor we're making.
Jump into
And
the deep end.
oh yeah, it was a mess. So I was given this 2-inch rod stock of 304 stainless. Had to cut a piece off and turn it into a rocket nozzle, and that took so long. I tried to cut it off part of the way in the lathe and part it off, but the thing's so old and crappy you can't. Parting stainless in a lathe from the 40s in that condition is obviously a mess, and I had to like hacksaw through the rest of it. And the whole thing was machined with one of those brazed carbide tool sets from Harbor Freight. You know, those those really crappy, like, it's just super spindly rubber boring bars, the brazed
Right.
carbide. And I mean, eventually it got done, but it was, yes, jumping into the deep end is a very good word for it. Um, so that was sort of my foray into that.
And it
And
didn't
then
scare you off.
it
That's
didn't
kind of
scare me off because I
that's a
mean
good thing.
it was awesome. It was so fun. Like, even though it was like really difficult, like machining's like super fun. I think most people can can agree
I
with
would
that who
agree.
are
Yeah.
listening. And it was dope to like take this chunk of metal and turn it into this like shiny rocket nozzle that I had like only ever seen pictures of stuff like that in books and whatnot. But that definitely got me hooked. Um, that rocket never did fire due to some other safety concerns that were brought up about other parts of it. But throughout the rest of high school, I kept doing work for them. We did make a few more better engines with some graphite nozzles that ended up firing. Never made it to space, funnily enough. I don't know. I don't know why. It seems like a pretty reasonable goal, if you ask me.
I'd love to say I'm shocked, but there's a YouTube video. I think it's, what is it? USC was the first student one
Hmm.
to go to space,
Yeah, that
and
was super
there's a whole
impressive.
documentary about getting there and like them failing once and all that stuff. And
Yeah.
yeah, after seeing that, I'm like, oh yeah, that's a extremely lofty goal.
Yes it was. But I mean, you set the extremely lofty goals, and even if you don't achieve them, they're going to force you to learn a lot along the way. That's sort
Oh,
of
I bet.
what we figured out through doing that. The failures were great as well. I've got a couple of videos on my channel of rockets blowing up and whatnot. Um, that happened more often than I would care to admit, but that sort of got me into it all. Fast forward to college, the rocketry thing sort of fell apart after high school because everyone in that group was a high schooler, and then we all graduated, and I was like, well, this has been fun, bye. um, so I went off to Auburn studying aerospace engineering because that's what I was interested in, of course, and
What made you
joined.
choose Auburn? Was it, are they known for aerospace or?
They've got a very good engineering program for sure. It was between, honestly, the decision was between them and St. Louis University. St. Louis University has another very good, not only engineering program but rocketry team as well. Um, Not that, I think it's kind of absurd to say that my decision was based on the quality of the rocketry team they had at the school. I can't say that it was, but it definitely was on my mind. But yeah, I mean, it was close to home. The price was decent. They gave me more money than anyone else, so that's the real factor, isn't it?
Yeah, that helps a lot.
Yeah. But yeah, that ended up there and did rocketry for they have a team there. Did that for a little bit, but definitely was missing machining because that was the real like underlying passion at that point was yeah, I mean, this is cool, but I like to make like stuff out of metal. That's the fun part. Um, and then out of the blue, probably about 1 or 2 months into college, an email blast got sent out by our advisor, and it was like, "Hey, there's this new makerspace opening up on campus. Um, they're looking for people to work there, and go to this meeting at this time if you're interested." Pretty vague, but I had been involved in the makerspace in my hometown, and I was like, okay, well that's a good gig. Maybe there's maybe there's money involved, maybe there's not. Either way, it seems like this would get me access to a shop, so that would be fun. Um, so I showed up to this meeting, and basically this was where I sort of compare my story to what to what Robin Renzetti says about being at the right place in the right time, and that's that's just sometimes you get very lucky with that sort of thing. So basically, they just opened up this, not even opened up, they had built this makerspace in this brand new building on campus, had all these amazing facilities and tools put into it, and then we're like, okay, well, we can't do anything until there's people to work here and we figure out how to run this. They just spent a bunch of money on a bunch of tools, and then we're like, well, now what? So the meeting was like, hey, we need people to work here. We have a prototype shop with a bunch of 3D printers and laser cutters and all this stuff. We got a metal shop, cool welders, and a wood shop, and this huge big workshop area. And then there's a machine shop too. So we took a tour of the thing, and the machine shop was like, it's not big. We don't have a ton of stuff in there, but I mean, everything was just brand new. Like they had spent millions of dollars on this place and dumped a bunch of tools in there, and like I mean, stuff was like still in boxes. Like nothing had been touched. Like the
That's
machines
awesome.
hadn't even been fully unpacked yet. And they were like, "We need people to run this place. We don't have anyone." And I was absolutely honest. I was like, "Look, I don't I don't have almost any machining experience. Certainly no CNC experience. But I've made some parts on a lathe for like a few years, you know. That's and then, honestly, that was the thing was that was the most qualified person
Out of the
that was
people
at that
there.
meeting, because I mean that's not super common for like a bunch of freshmen in college to have any machining experience, frankly.
Right.
Um, and he was like, okay, the guy in charge, our boss, was like, all right, well, you and this other kid who this is my coworker Nick, who was in a similar situation. Okay, you guys can figure it out. We're aiming for opening to the public in like a year or so, and we just got to get set up and get everything running. So that's how we got that job. At first, it was just a volunteer position, um, literally like taking stuff out of boxes and organizing things and figuring out um, how to run it basically. And then after a while, it turned into a paid position, and now we work there. So it was again to go back to the trial by fire idea. Like so the machines we have in there, we've got one of those Jet Elite Series manual mills, which I love. Trax lathe, I think 14-inch swing or so. Um, Haas Mini Mill 2, big old dual bandsaw, and a enormous Omax water jet.
Oh,
So
cool.
not like a bunch of equipment, but all the equipment you need really, um, and obviously all the other tools and metrology stuff and that sort of thing. But again, like at this point, I had run a small crappy lathe in my garage, and you know I tried to turn my drill press into a mill. That didn't work really super great, obviously, back in high school. But that was the extent of my milling experience, and I had never run any of these things before. And then suddenly we're like tasked with like he's saying like, okay, well when we start opening, you're gonna have to be training people on how to use these machines that I've never used before, and that's just a terrifying prospect.
I was gonna say, yeah, sounds a little terrifying.
Yeah. And honestly, like probably not the safest thing in the world, but what that meant is we had to figure it out before before we opened. So, and especially with the CNC as well, I told him I was like, look, I may know some stuff about manual machining, but I've never touched CNC. Like not even the little desktop router thingies, like just no knowledge of it at all. And he's like, well, you're interested in it, right? Yeah. Well, then figure it out because no one else is.
That's awesome.
And oh yeah, so over the next good while, we learned how to use the machines. And this is really credit to YouTube here because frankly, that's where all of my education has come from, is the YouTube machinist community and Insta machinists and all that. Like, no, there was just, especially at our school, there's no formal like training program you could go through apart from one class for the mechanical engineering students. But, you know, John Saunders taught me Fusion 360. Um, people like you get to go way back. You A Bomb and Mr. Pete and all that taught me the basics of manual machining, and then you have you go deeper into the rabbit hole and you find all the smaller channels that are really good at other things, and frankly, you don't even need like tutorial video. If you just watch enough machining content, like if you just watch Adam Booth run a lathe for, 8 hours, you're just gonna like sort of by osmosis, like you're gonna see him and see little things he's doing, and it's not gonna be all the education you need, but you learn a lot just by watching. Um, and that's what we did. And then we hopped on the machines after we gained a little confidence. We made some parts, and our boss was super generous with this. He was like, "Look, like as long as you're learning, like we just need you to like get good at this. So like even if you're not explicitly like organizing a cabinet or something, like you can still we'll still call it work, right? Because you're figuring out how to do this stuff." Um, and we learned how to use the machines. Um,
That's epic. That's really, really
yeah.
cool. So then how did you get to your summer internship this summer?
Right. So I was talking about how, I can consider it like a journey, a continual progression, getting into machining things. So, as I continued to make stuff, I just always had this desire to like make stuff nicer. And I want this dimension to be held even tighter. And because you make things that require these dimensions to be held tighter. And I want the surface finish to be better because it looks nicer and more professional that way. And I just always had this, you know, lusting for higher precision stuff, even after because machining is sort of the pinnacle of like the making stuff mountain. Like below it, before it, you have all your woodworking and your welding and stuff, and then machining's like, okay, this is the ultimate for making stuff really, really nice and really, really accurately. But I got to the top of that hill and was like, but what if we just like, I want to go higher, like,
Right. You get to the top and you're like, oh, there's another peak just right over there.
Exactly. You keep finding out that there's more peaks. You're never really to the top. Um, so as you know, as we were learning and machining and doing all these projects and whatnot, I kept getting into this higher precision stuff and wanting to get better and better. And this is sort of how I discovered, air bearings. So I think I found out about it first from Ben Krasnow's video on it, Applied Science. So he did that video on the graphite air bearings made with no special tools or whatever, sort of lapping them with the shaft that it's going to run on. And I was like, okay, this is dope because one, it just looks cool because it's frictionless. Two, it's something that enables you to be really accurate. And then almost immediately after, found the infamous Dan Gelbart video that everyone knows and loves. At this point, I'm assuming that everyone's seen it. So I saw that, and he was like, "The secret is air bearings, basically. Like everything's on air bearings." I'm like, "Okay, well, we need to get into air bearings then. This must be the secret." Um, and so I started trying to make air bearings. Got some graphite off McMaster and some off of Amazon as well, and just put some air behind it and made a flat surface. And oh wow, it floats. That's cool. Well, now let's make one that can spin. And then tried to make reamed out a hole in the graphite thing, and then made a shaft that was very very tightly matched to that hole. So then it floated in there. And then I was like, okay, well this is neat, but we need a spindle because that's what you need for these high precision lathes like Dan Gelbart has. So we tried to make a spindle. I mean, and really not knowing very much. It was just like seeing stuff on the internet and being like, okay, well this is the idea. And I looked through some literature that New Way had, but there wasn't a bunch of stuff out there at the time. And through that, we sort of got introduced to the higher precision level of all this and precision engineering in particular. So this was sort of the issue I was running into in college was my interest in machining always came from I liked designing and building stuff. And if you like doing that sort of stuff, when you go to college, what do people tell you to do? They tell you be an engineer because that's what they do allegedly. But quickly realized like, wait, no, there's this whole divide between the machinist and the engineer. Like that's this classic like rivalry almost, and that's not what I wanted it to be like. I want to design the thing, but then make the thing, and so I started realizing there was this divide, and they separate, but where they come back together is, climbing this mountain, precision engineering and the field of precision engineering. Because in order to engineer and make stuff that can have micro-inch, even nanometer accuracies and all this stuff, you also need to be very very familiar with the manufacturing processes and how stuff gets made and how to design things that are makeable but can also do what you need to do on a nanometer level. And so got sort of acquainted with that field, read some of the classic texts. Slocum's Precision Machine Design is a great one. Of course, Foundations of Mechanical Accuracy is, the Bible, basically.
Right.
But got really into that field. And during that summer, I got an email from some dude who had watched my YouTube videos about air bearings or whatever. This kid Andrew, who went to Ohio State, and he was like, "Hey, I'm a mechanical engineering student here. I'm also like really into precision stuff. I work in a machine shop here. Um, and like we just had a lot of he sent basically just this huge rambling email about like this is like this thing you're doing is cool. Like, have you heard of this? And also, this is really neat. And I read it and I was like, oh, this is awesome. And then we hit it off really quickly. And he was like, hey, by the way, I found this thing on the internet. There's this like precision engineering student challenge or whatever, and you should look into it. And basically, it was this like this thing for college students where you had like a machine that you had to build to, and it changed every year, but that year you had to make like diffraction gratings with a single crystal diamond tool, and whoever made the best diffraction grating won. And I was like, oh,
Wow.
this is pretty sweet. um, this would like be a really good test of all of my abilities and interests and stuff. So I like go to dig into it more, and it turns out, oh, we missed the registration for that year. It was already too late. So I was
Bummer.
like, oh, that's too bad. But what's this thing that where is this hosted? Like, what is this organization that's running this? What is this ASPE thing? And that's the American Society for Precision Engineering. And we looked, and the finale for the student challenge was held at the annual meeting, which is the conference they have once a year for ASPE. And we were like, whoa, like we can't do the student challenge, but this conference looks pretty sweet. Like they've got all these companies that we've heard of there. There's some really cool talks going on. The keynote speaker was Ray Weiss, the dude who got the Nobel Prize for the LIGO thing. There was just
Oh
some
wow.
really interesting looking things, and this was a conference like at the end of October or whatever. And we were like, what if we went? Like this, like it looks really cool, and like I've never been to a academic conference before. Like, but like, look, Kern's gonna be there, Interlight's gonna be there, like all these people we know are gonna be there. What if we just like show up to it? And so we did. Um, Now we had, and when I say we, now I'm talking about my coworker Nick and I. Nick's also interested in the same stuff as I, and we were the two that were like, let's just take a week off of school and run over to Minneapolis real quick because that's where it was being held this year. Um, and we showed up, got there by the skin of our teeth with sky miles and hotel points and spending way way too much money. We were like, it's a cool opportunity. Like, let's just splurge and go check this place out. Um, so we showed up at this conference, and everyone's like, "Who are you? Like, who's your advisor? Who are you here with? Like, what professor are you guys with? What's your what graduate school are you in?" And we're like, "I'm a sophomore in aerospace engineering, and we just came here." And everyone was like, "Who are these kids?" Like, that was basically. Um, Now we had heard of professional instruments, obviously through all of our research and whatnot, and I had been through their website before. And if you've never looked through their YouTube channel, that's a that's a blast to go look at all those clips. Um, but they were there they had a pretty large presence there because they're also based in Minneapolis, obviously. Um, and so during one of the vendor expo things, we were walking around and got to talking to them. And senior engineer there, Byron Knapp, was like, "Hey, you guys should ask for a tour. We've been running tours this whole conference because we're like our plant is like 15 minutes away from the conference center. Like, so we've just been shuttling people back and forth. Um, so he's like, go ask Dave. He's the man in charge. You got to go ask him for a tour." And he wasn't able to do it at the time, but he was like, Henry, like this is his son. That Henry, you go give these guys a tour. So we just got into this dude's car, and he took us over to the place and gave us a full like over hour long just tour of the entire facility. And I was like, okay, this is the coolest thing I have ever seen. Because I don't know, PI's got sort of a legendary status. Um, I feel like just because of what they're able to do and the environment they're able to do it in. I feel like a lot of when you think of like ultra precision spindle manufacturer, you think of, you know, super clean, lean German shop with multi-million dollar machines everywhere, and everyone's got their German little lab coats and just super high end fanciness. And not to say PI is not; they've got some very amazing machines, but it's like it's not this crazy operation that a lot of people imagine when they think like ultra precision. Um, so I was just like, this is amazing. That's where my profile picture comes from. Is I got to see my first Moore machines there, so I took a picture next to a Moore measuring machine. Um, but we continued talking to them throughout the rest of the conference and told them about this lathe that I had been working on, which I guess we'll get into in a little bit. Um, but but hit it off basically. We kept in contact with him after the conference, and then sometime in the spring, emailing with Byron, he was like, "Hey, would you guys be interested in coming to internship over the summer?" And we dropped everything. Like it was just this out of the blue like PS in an email, and we were like, "We're there. Like whatever it takes, we are there." Because just I mean, this is like the Juilliard of grinding basically
Right.
and precision machining. You're not going to get a better education than that anywhere else. So we dropped everything quite literally and found a way to get up here and drove over the course of a few days from Alabama to Minnesota, and that's what I've been doing this summer basically. It's working here.
That's great. What an experience and opportunity.
Yeah, right.
Well, this is probably a great time to get into some of these questions. We had a bunch about your lathe that you're building, and then a bunch about your internship. So let's start with the lathe then. NH Micro asked, tell us about the diamond turning lathe. Why did you start the project, which you kind of alluded to? What are the goals? What have you learned along the way? Mercury PGH also had questions about the air bearing spindle lathe copy. Want to know more about progress, and if you plan on releasing any of the drawings, or if you've talked to Dan about any of the design.
I wish. It seems like no one's able to get a hold of Dan Gelbart for whatever reason. But yeah, I mean, I would pay so much money for him to do like a 3 hour long video just going over every single detail of that lathe in like meticulous detail. But yeah, so the lathe project sort of that started over the COVID summer actually. When I was cooped up in the house. And so again, going back to the aerospace thing, I've always seen space is my jam, right? So I was also into astronomy a little bit and telescopes. Not like not enough to say it was a hobby, but I had a telescope that a friend had given me when he moved off somewhere, and I'd looked through a nicer telescope at some other event before, and it's pretty neat. Like I don't know if you've ever like looked at the moons of Jupiter or the rings of Saturn through a telescope, but I find that to be absolutely like just mind blowing to look through a to look at the sky and there's like a planet and you can see like five moons orbiting it and it's got stripes on it and stuff. Like that's like a real thing that's up there. That's pretty impressive that you can see that all those millions of miles away. So I was looking through my telescope a lot and I was like, you know what? This fuzzy blob with dots around it is neat, but like I want better. I want to really see these planets. So I'm like, what if I made my own telescope? And that's kind of an ambitious thing to just try and do. And looked into it, and there's this whole community of homemade telescope makers that lap their own mirrors by themselves and do some really impressive work, honestly. But it's all by hand, and I wasn't really a fan of the non-deterministic nature of it, where you're just, you rub it for a while and then you measure it and you hope it's the right shape. And yeah, it self generates a sphere, but really then you got spherical aberration. So really you'd be better off with a parabola or something. So, and you can make A spheres, but again, it's just sort of like hand wavy. It's an art. It's an art more than it is a science.
Right.
But of course, through all my, research and what I've heard described as rabid autodidactism, I had run into, diamond turning machines and, single crystal diamond tools and all these just amazing finishes you can get with it. So I was like, well, what if I made a really, really accurate CNC lathe, just like Dan Gelbart, and I wonder if you could just use that to just turn mirrors, like just have it cut out just a perfect telescope mirror, boom, ready to go. You don't have to lap anything for months on end. Like, I wonder if I could just make one of those. I was like, well, that'd be really hard. It's got to be really, really, really accurate. Because I mean, the accuracies of these mirrors, they're in the they're measured in the form. Accuracy is measured in fractions of lambda,
Right.
lambda being the wavelength of light that you're looking through. So I mean, lambda over 20 mirror, which is a really good mirror. Okay, well that's 500 nanometers divided by 20, and the thing's got to be
Right.
accurate to that. That's a tall order for sure. I'm like, well, maybe I could just start out with like a CNC lathe that was like pretty accurate, and then tune it to go from there. And frankly, the issue at this point was I had no idea what was involved. Like, just complete ignorance, not complete ignorance, but maybe Dunning-Kruger would be a better way to describe it. like like I had some idea of what was necessary, but not enough. And so I start designing this thing. I had these really nice Gilman slides, these dovetailed slides that I'd found a while ago. Like, well, I'll just put really accurate, like, servo controlled stepper motors on there with closed loop feedback, and then I can micro step them real small. Oh, look, I can get like I can get in theory 4 micro-inch steps with this system. Oh, that's pretty good. I could maybe make a lathe like that, and designed some stuff with that, and then it's like, well, the real key here is air bearings, as we all know. You need an air bearing spindle because that's how you get those really good finishes. So you need completely smooth motion with no noise or rumble from any rolling elements. It just needs to be perfect rotary motion, basically. I knew that much at least. Um, then again, Dunning-Kruger. Oh well, I'll just make my own spindle. How hard can it be? I'll just do it myself. And then spent a long time trying to develop my own air bearing spindle. Um, and this is all on my YouTube channel and stuff. Came up with a neat little system of having some sort of free floating radial air bearing pads that had all their rotary degrees of freedom so they could self align to these thrust plates on either end of the thing. I won't go too deep into it, but I came up with a design and started developing these air bearings for it. And went to the conference probably around, around this time. And this is when we were telling everyone about this project. Like, well, I'm trying to make this really accurate lathe. And here's what I'm doing. I'm trying to make my own spindle. And I told PI about this, the air bearing spindle people. Like, no one makes spindles better than them. And they were like, no. Like, no. Make everything else yourself. Like, make hydrostatic ways, make the whole machine structure, make everything else, but don't even bother with this spindle. Like, get one of our spindles and do the rest yourself. Like, the spindle is not worth wasting your time on, because, and frankly, and they're right. You're never gonna get a spindle as good as a PI spindle. Like I could work for 10 years on making a spindle. It's not. It's just not gonna be the same. They really are the best.
That's got to
And
be pretty heartbreaking to hear, though. Talking to the authority, and they're like, "No, just don't."
yeah, I mean, I kind of like knew like deep down like, all right, well, it's it may spin, but yeah, I knew the error motion wasn't gonna be anything as good as theirs. But hearing that, I was like, yeah, I guess that's a good point. I wasn't super bent out of shape about it because I'd learned so much through the process, and that's really the main thing, right? Like what Robin says, if you want to learn something, you just do a project that requires it, and then, well, guess what? You're gonna have to learn it.
Right.
So after that, after the conference, I was like, well, that's kind of a bummer. But they then reached out over email and was like, hey, remember we were like, don't make your own spindle, use one of ours. We've got a couple extra spindles. You want one? And
Oh, how cool!
I was absolutely blown away by that because I mean, the if you know anything about the spindles and how high end they are, like these are not things you just give away. They're not you're not gonna find these things at the dollar store. You know what I mean? But they were like, yeah, we've got a couple extra of these spindles that the story was they had made them for a customer a long time ago. They're not their standard product. They're like a weird custom job. And the customer was like, actually, we don't want these anymore.
Oh,
And so they just had them lying around because they weren't standard product that they could just sell off. They were just these weird bespoke spindles that they didn't have anything to do with. And so they gave them to us, which was pretty neat. And that really kicked it into gear there, the whole project, because before that it was like just a personal like I'm just doing this thing. It'll get done when it gets done. Like there's nothing writing on it. But now it's like, okay, well, the best air bearing spindle manufacturer in the world just gave you spindles
right.
with the intention of you making this machine. So you better make the machine, or they might not be super happy. Like, yeah, it's going to be hard, but you better figure it out because they just gave you a lot of free stuff. And it would be pretty embarrassing to just be like, I'm not really doing that project anymore. Sorry, guys.
And so this was before your internship.
Yes. Yeah. So the conference was in the fall. They sent the spindles after that, and then kept chatting with them. And then in the spring, they brought up the internship thing. The other thing they mentioned at the conference was they wanted to see, a bit more like they were like, you should make this a little more formal, like make it into like an actual research thing. So maybe you can get a couple bucks for it. Just to formalize it a bit more. So it's not just like a garage, like random dude bozo project. So we in the spring we applied for undergraduate research fellowship at school for this machine. Um, to again just to formalize it, being like, here's the project, here's what we're going to try and do. Like these are the particular research areas we want to look into, and then it also forces you to set concrete goals. So
Right.
officially, the goal is to make this machine tool that can produce parts 8 inches in diameter. It's got an 8-inch swing, partially motivated by the fact that that's like a decent sized telescope mirror.
Right.
But 8-inch parts with a form accuracy of less than 1 micron. So across this large aspherical surface, everything's accurate to less than a micron. Pretty I mean nothing like single digit nanometer, but that's
Even
still a
just like measuring that is going to be
mm-hmm,
a
mm-hmm.
challenge in and of itself.
Oh yeah, and the metrology is a whole other rabbit hole we can get into, but yeah, less than 1 micron form accuracy and sub 10 nanometer RA surface finish. So less than half microinch RA, and that's where you start to get into the what's defined as an optical surface finish. Surface finish is a another really messy rabbit hole to to get into, and like what is a good surface, because you can't just define it with like an RA. Like there's so much more to it. There's so much nuance, and like you can have a really good RA finish and it's not as shiny as this other one with a worse finish, and
Right.
but
Well, I mean, I tell people
essentially,
all the time that like RA is just an average.
hmm
Like if you want to know how good your surface is, RZ is a much better measure because that's
right,
total deviation.
right,
But yeah, I've seen surfaces that technically are 63 RA, and it's like, well, it looks rough. Like
yeah, yeah,
but it's an average, so it's because it's evenly rough. It's a good RA.
hmm hmm So that's, yeah, that's a bit harder to quantify. But for now, we just said, okay, less than 10 nanometer RA, because yeah, there's a lot of other factors, but if you're less than 10 nanometer RA, chances are it's a pretty darn good finish.
Yeah,
So it needs to be of an optical quality is the gist of it. Um, Especially for if you're going to be making telescope optics or whatever. But the idea is that, it's not just for me making telescopes. It's going to be a tool for the university to have for research use, for even just for helping out other departments. Like, you could order a custom optic, like a weird custom mirror you need for your research from Edmond or whatever. That's going to be thousands and thousands of dollars and going to take who knows how long. But what if you had the ability to just like make it yourself,
right.
That'd be pretty powerful. I think so. Um,
So did it get accepted? Are
and
you
it did, yes. So
awesome? Congrats.
we were just recently before the summer awarded this fellowship to do this project. So now we got two things, forcing us to do it. We got the fact that PI gave us stuff, and we got the fact that now the university is giving us some resources to do it. So it's going to get done.
Awesome.
Uh,
So how has the plan changed then? Are you going to go to a different
Absolutely.
motion control and things like that?
Absolutely. So the original project that I came up with over the pandemic is there's very little of that remaining in the in the current design, just because of all the one things that I've learned since then, and two resources we've acquired. Basically, like now it's going to be built around these spindles that PI gave us, obviously, um, and the current designs using a hydrostatic boxway design with linear motors and all the good stuff, basically.
Very
Um,
cool.
I don't know. Yeah, so if you look back at some of the decisions I made on that original design, it's you don't know what you're thinking when you look back. You're like, oh
Yeah.
come on, dude, that's so not gonna give you what you need. And
Well,
I'm
you're
sure in
budget
six
constrained and
yeah,
all that.
in 6 months from now, I'm sure it's gonna be the same way. I'm gonna look back and be like, oh dude, what? That's not how you're supposed to do that. But you gotta learn over time. It's a process.
What's going to be the control system?
So the control system that's still sort of like up in the air, if you will. We've looked at some aerotech products that are pretty intriguing. The cam side of things is going to have to be custom.
Yeah.
And when I say custom, I'm like written in MATLAB, like a cam software kind of a deal. And this is a thing that Marv talked about when he was on here and making the shiny spark. You can't you can't use traditional cam systems for this ultra precision work, because it takes your nice freeform surface that needs to be accurate to less than a micron, and it turns it into a mesh, a big old
Right.
blocky low poly mesh. And you can turn the tessellation way up, but then your toolpath's going to take 15 hours to calculate if it doesn't crash. So it's the motion control. It's not going to be like any traditional cam system. It's going to be like, okay, you're going to mathematically define this this surface you want, and it's going to like calculate it like completely directly. There's not going
Right.
to be any like no 3D model, no conversion to mesh or anything. It's like it's going to follow a defined mathematical trajectory with you got to take all, because all of those other things are just sources of error.
Oh yeah. Well,
You can't have
did
it.
you hear the most recent Precision Microcast? Plugging for Josh, who asked one of the
Oh yes,
questions.
of
But
course.
it was with Christian Wenzel from
Hmm.
Innolight, and they were talking about. I couldn't believe some of the numbers they were saying, like 100
Oh yeah.
kilohertz loop
Hmm.
on their motion control and stuff, and then yeah, all of that, cam is baked into their lathes basically.
Yeah. Yeah.
So
So we've got the servo drives we have, and we're planning on using. They're not quite that good. I think they're 20 kilohertz servo loop, which is, it's all right. But again, we're to compare it directly. Like this is not a competition with Innolight. Like we're obviously that's on a different level entirely. Yeah, we're trying to make a ultra precision diamond turning lathe, but I mean nothing, nothing even remotely close to the stuff that Innolight and more and Precitech can do.
well, it sounds
Um,
like you're on the right track, though. I mean, it must have been kind of confirming, hearing all of these things, and you're like, oh yeah, we were going to do that, and like we're going down that road too.
yeah, yeah, absolutely. It's been very cool to get to sort of interact with some of those people who are have done it basically at ASPE and all that. Like, well, like here are the things like practically. Here's what you need to know. Um, but yeah, it's the idea is similar, but I'll tell you right now, we're not going to have zero point zero 0.01 nanometer programming resolution because because that's what like those Moore machines. That's what they operate off of. Like you can program a move of 10 picometers, which is you know
Insane.
uh, it's subatomic, literally. It's smaller than any atom. That's like unbelievable. But yeah, that's the idea. Yeah.
Well, now that we've talked about the lathe, let's talk about your internship. Josh also asked, interning at PI, what are some of the things about their processes uh, that surprised you, and what can you take away from their approaches to precision?
Yeah, that's been a really fun learning experience, getting to see how they've done all that stuff. Um, the main thing I would say though is it's not like it's not rocket science. Again, like people think it's this. People have these images in their head of these crazy multi-million-dollar machines, like super high-end factory or whatever. But there's a few fundamental principles, some easier to implement than others, that I think get them where they want to be. One, well, okay, I can start with the simplest and most powerful is, air bearings on all the things. Like they really are like a just fix all. Like they'll buy grinders, they'll put air bearings on them, and boom, you're gonna be able to put out parts that are just as accurate as the best, multi-million dollar Studer grinders that you could get. Like the air bearings are literally like a magic wand for for accuracy. If you if you
That's really cool.
if you have your spindle on an air bearing and you have a rotor grinding set up with an air bearing, you're you're just limited by really the straightness of your ways um, over the distance where you're traveling in the rotor grinding, and that's honestly on most all grinders. That's really not the limiting factor. That's one of the precision, the 50 tidbits. I don't know if you're familiar with those on the PI website.
I don't think I've gone through all of them, but I have looked through a few of them.
Yeah, that would be another good thing I can suggest. If you just Google professional instruments tidbits, there's a blog post on one of their old websites. That's not their main active website anymore. Um, and it's just 50 things. 50, I mean, the name says it all. 50 little tidbits to help you, get get the accuracy you want. Um, and I've got them right here. Number 28. Most machine tool slides are very well made. The biggest deficiencies in most machine tools are the work spindles and their tool and work holding. Um, and that is absolute. That shows up in everything they do. The grinders are rarely the limiting factor as long as you know what you're doing with work holding and you have a really high accuracy spindle and rotor grinding spindle. I mean, you're going to be able to hit some crazy, crazy numbers. Um, but of course, not everyone can just slap air bearing spindles on their machine tool. That's not really practical for for the home gamer.
I wish, but yeah,
Yeah,
you're probably right.
yeah, unfortunately. But the other things that I think are pretty valuable, that's not on the tidbit, is they've always been a big proponent of every man is their own QC department. There is not there is not an inspection department at PI. There is no guy who's like the inspector. There's no QC that like as its own entity. Every person like who's running a grinder, one has the tools and also the ability to inspect the parts that are coming right off the grinder and making sure they're good. Because in order to hit those levels that they're at, you can't have a super long feedback loop of okay, we make a part, goes off to inspection, gets inspected, and then like comes back, 2 hours later. Oh, by the way, those parts you made earlier were bad. Because
Right.
at that point, you're, I mean, your machine's warmed up a little bit, and now the situation's completely different than it was when you sent those parts off. So you need to have a very tight feedback loop to have that be a sustainable process. So all of the people, running these grinders, it's kind of neat. I've got a picture of it, I think, but like you'll have a grinder, and then right next to it there'll be basically a miniature inspection station, a table with a surface plate built into it, and a air bearing spindle to inspect circular flatness. And then some of the other grinders have straight line flatness testers. Um, Everywhere you look, there's microcators. Like they're just they're all over the place. Um, but that's something they've always pushed, and I think is probably a pretty powerful thing if you're running a shop, to have every person be capable and competent at inspecting the parts to the level they need to be inspected to. Um,
Definitely. So will they call over other machinists if they have, if they want a second set of eyes or something like that?
yeah, that's definitely that happens. But I mean, for the most part, these guys are, and it's powerful. They're not just really good grinder operators. They're really good at metrology as well. Um, and that's really the key. I guess suppose that tip is more applies to a production setting. Um, if you had to come up with a takeaway for that for the home gamer, I guess it would just be get really good at metrology,
Yeah,
because that's just as if not more important when working to these levels, is not not running the machine, but how do you measure it good? Because if you can't measure it good, there's no point.
yeah, I completely agree. I've said numerous times, I think, on this show that like my year and a half, 2 year stint in the QC department at my last job, I learned
Mm-hmm.
more about being a good machinist than I did as
Mm-hmm.
being a machinist in the years
Yep.
prior. Because you
Yep.
learn all the little, oh, there's a tiny nick at the bottom of that bore that, like, as a machinist, I would have run 5 parts and not even noticed it. But as a QC person, you're like, oh, I'm paid to notice that kind of stuff.
Yeah. Yeah. And the other thing is, I think speed as well. Because like, yeah, if there's another QC department, you can just churn out parts and send them over and not think about it. But if you're being forced to, after every part, you take it off and you move it and inspect it and look at everything, every single part. Yeah, it's not the quickest workflow ever. It's not super speedy, but it's sometimes you need to slow down to go fast, right?
Hmm.
Uh, one of well, one thing that's kind of hilarious is they're really proud of their what they call lard manufacturing. So like the opposite of lean, that's what they call it, is lard manufacturing.
I
It's
like
not.
that.
I mean, Jay Pearson would have a stroke if he took a tour of this shop. I'll just put it that way. But it works, because for stuff like this, you can't have a crazy, you're just like crazy throughput, like just moving hundreds of parts a day. through these grinders, like you have to go slow.
Right.
Um,
Well, I'm sure there's not the demand to support lean manufacturing. You don't need to make
Same thing. Yeah.
10,000 spindles if you only have a demand for 1,000, or something like that.
Yeah. And that's the thing that enables them to do that as well is, yeah, if their prices were, if you could buy a spindle for $500, everything would fall apart because there'd be so much demand that they would just not be able to deliver,
Right.
like at all. Um, that's and this is something that's interesting is the flat stones um, that they make. That's part of the reason the price is so high is because if the prices are low, then you just get you don't make that much money on them because a lot goes into making them. Um, I know, I mean, most people have seen Robin's video on making the flat stones, but the way PI does it is pretty different. They're more flat than anyone else's stones. I can say that with a very high degree of confidence. That's just but I mean that's to be expected, right? Um, but yeah, if you had a huge demand for those, it takes it takes away bandwidth from the actual like money making products, and you're not going to be able to make them as good. So that's part of the reason the prices are so high is just to like literally like keep the demand to an appropriate level, and that lets them make them good and also make money off of them.
Right.
But
What about managing thermals? Because I imagine, I think that that's a problem for every machinist, whether, you're working in tenths or in micro
mhm.
inches. So have you learned anything special about how they manage thermal growth and how they deal with that in that kind of environment?
Well, honestly, I was surprised. There's not as much of that as I would have thought. There's a lot of it, but there's the whole idea of the environmental control and like you have these inspection labs with like our HVAC keeps this room plus or minus a hundredth of a degree year round at 68 degrees. Don't see that at PI. They've got an air conditioning system. It keeps the shop you know not hot, but at the 68 thing, that's not really held very tightly in a lot of places. The way they achieve, precision without having the crazy environmental control is one, there's of course the thermal control for the machines themselves. So, aquarium heater in the coolant tank to keep the coolant temperature constant. That's a classic, if you will. There's the light bulb in the casting. They'll put like 100-watt light bulb or something up inside the casting, and it's just always on. And it will, you can either have it always on, or you can have a thermostat to try and keep the machine frame at a certain temperature. And then take that one step further. Some of the grinders they have actually have big old heating pads on the column, sort of similar to the jig bores, the more jig bores that kept the spindle housing at like 80 something degrees or whatever it was at all times. It's like pre-warming the machine because there's no
Right.
use in trying to keep the machine at 68 degrees because it's not going to stay there, and then you're going to get hot spots and cold spots. So if you just sort of like warm the whole thing up, it ends up being more consistent that way. Um, so that's the machines, and then for inspection, and this is the thing that they like to show off on tours and stuff because this is real neat. Some of the grinders, where you have to do really high precision stuff, you've got your metrology station next to it. Part of that metrology station will be a insulated aquarium tank with big old foam on all sides of it and a fluid in it that has, it's not just water. It's got like rust preventative and crap. And then an aquarium heater connected to that. So you've got this big old water tank that's held at a very, very consistent temperature, because it's a lot easier to hold a tank of water at a temperature than it is to, have a whole machine shop be 68 degrees.
Right.
And all of the metrology equipment that they use, like their reed mics and the gauge blocks and everything, are in this tank. There's a surface down at the bottom of the tank that's filled with liquid, and they take the parts off the grinder and they'll put the parts in there. There's even ones with, like 60-degree centers, all underwater, all submerged. And all of the metrology and measuring and stuff will take place underwater, submerged in this extremely thermally consistent liquid environment. And the other thing that helps with is the soaking, because I know Robbins mentioned letting parts sit overnight before he even measures them to come to an equilibrium with the environment. But if you just put it in a tank of water with a thermostat connected to it, that's gonna that's gonna come to an equilibrium way faster than letting it sit out in air. It's gonna pull all the heat out of the part and get everything all nice and consistent. There's no gradients or anything, so it's really efficient in that regard for keeping everything stable. But that's a when I first saw that, I was like, oh dang, they're like serious, because there's like this huge insulated tank with measuring equipment in it, like just all like submerged gauge blocks and centers and everything. It's all in this little, and the fluid's got like a weird green tint to it. It reminds me of like the like in a sci-fi movie, like you got an alien in one of those big tanks.
Uh-huh.
It's but that's a really neat way of making sure that thermal's just, it's not even a concern in the metrology process when everything's underwater.
That's
Um,
crazy. Yeah, I never. It makes up like total sense when you say it,
mhm.
but I never in my wildest dreams would have been like, oh yeah, 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 let's put all the metrology stuff underwater. That sounds like a
Yeah,
good idea.
yeah,
That's really
and
cool.
and the stuff that isn't, like in there, there's like a room with a lot of metrology stuff, and I wouldn't call it like an inspection room per se, but there is one room that has like their microscope and whatnot in there, and the comparators and stuff they've got in there. There's little notes on it, like because there's a thermometer right next to the gauge blocks that you're measuring, so you can see how hot everything is, and say like if it's this temperature, multiply your measurement by this number, a little correction factor. If it's this temperature,
Wow.
multiply it by this number. So you don't need to hold it perfectly stable. You just need to make sure you're keeping tabs on everything.
Right.
Like as long as you know what temperature it is and everything is at temperature, it's fine. You just got to apply a certain correction, and then it turns out fine. Um, but
Okay. What changes to your workflow specifically have you been surprised about? Because I imagine you pick up a lot of, tidbits that
mhm.
you've changed just how you work day to day. And I imagine that it has taken them some time to even trust you to work, anywhere near. So, what kind of things have you picked up that have made you a more precise machinist?
the Well, I think the main thing that I've picked up that, well, I've not had to change it here, but I'm going to change it when we return back to our shop, is I'm going to throw away all of our indicator stands. I know this has been touted by Stefan and Robin for a while, but yeah, I mean, having an indicator base in a arm that is just ludicrously rigid, like so overbuilt and so utterly inflexible. I mean, everything is, but
Right.
that really
Less of a
makes
noodle.
less of a noodle, less of a noodle. That makes a world of difference. Um, and it's not been something I've had to like adjust my workflow for there, because all of their indicator stands are amazing and super rigid. But it's something that definitely I'm going to change when we go back. Like if you have a Noga arm with the fine adjust at the tip where the indicator is held, just that no, you're you're not going to do any really really tight stuff to any level of repeatability, I guess that is, with something like that. um it really makes a world of difference to have good good indicator stands. But I mean, the besides that, I think the other, workflow thing that's really important is just ABS. Always be stoning, right?
I've seen that
That's
in the tidbits that stone your part, stone the surface plate, stone.
always be stoning. Yep. That's, I mean, precision ground flat stones are, they're magic. Like,
Yeah.
if you're not using them, well, you're frankly, you're wrong. You're in the wrong. You should be there. If you know about them and you're not using them, I don't know. You're crazy if you ask me.
I need to clip that
They
right
will
there.
do so much for your workflow and just repeatability and quality of metrology, if nothing else. And it's amazing. Like, if you have two stone, really really flat, really well stoned surfaces, um, which tends to be the case when you're like operating a grinder and you're mounting stuff up on the grinder. You've got your tooling plate on the spindle, on the rotor grinding spindle that you're mounting your part to, and you put your part on there. It's also really flat and been stoned off nicely. You just put a pilot to keep it centered on the spindle and a little drive pin on a feature that you can put some torque on it with, and you're all set work holding wise. Like, you can kind of just put parts down and grind them. I mean, just knowing, as long as you're entirely sure that there's no burrs or grit or crap, and you truly have two nice flat clean surfaces that you can put them, that nothing's going to rock or anything. I mean, if as long as you have a way to, you know, stop it from spinning and moving around on you, just in the plane that you're rotating it in, you don't need magnets, or a lot of the times you don't even need the super glue tricks to hold it down. Um, I mean, I don't even, I could not tell you the last time I've seen magnetic work holding used at PI to do anything that was of any concern at all. Like,
Wow.
if you're trying to get flat parts, leave magnets out of the equation, because there's they just stuff moves. Like, if you put enormous amounts of force, even if the face that's sitting on the chuck is pretty nice and flat, it's not perfectly flat.
Right.
Nothing is. So when you pull on it with all that force of the mag chuck, yeah, it's the thing. It's gonna move, and then you turn the magnet off. It's gonna move on you, so it's not gonna be flat anymore. They like magnetic work holding, just not used pretty much. There's one grinder that's set up with a mag chuck on it. That's like the tool room grinder, if you will, and it's tool room as in like just weird odd jobs where you don't the precision not isn't necessarily important, but everything
Right.
else, it's rotor grinding and either glue work holding or no no work holding at all. It's
Wow.
just parts
Just
on
like
a air bearing.
rung together kind of stuff.
Yeah, not quite, but almost. Yeah, just
Right.
that, just glass surface on one another.
That's cool. Another one of Kara Curry's questions was, what's the most precise grinder, and are the grinders vibrationally isolated more than normal?
Well, I mean, when you say precise grinder, they're all very good grinders. So, I mean, there's a bunch of Okamotos, um, Mitsuis, and Chevaliers are the three main grinder brands, I would say, that you're going to find there. Um, Pretty much all of them have 10 millionths downfeed on the y-axis, and for most things that we do, it's pretty good. That'll get the job done. Um, Otherwise, I mean, as I said before, the only real limiting factor from a machine accuracy standpoint is, the straightness of the ways, and frankly, they're all good enough. Um, they're all pretty darn accurate. So when you say precision, I would say, maybe we're talking about downfeed increments, and yeah, that's 10 millionths. All the rotary grind or the cylindrical grinding, all those, they don't have quite that resolution as far as infeed. So on those, we've got a lot of Heidenhain just glass scales set up just on the one axis, and then you can always use the hammer trick to to get those really fine infeeds. Um, but I mean, yeah, in general, 10 millionths is it'll get the job done because there's
It's pretty
tricks
good.
like yeah, there's tricks if you need finer than that. You can like on the I was doing some cylindrical grinding on some IDs recently, and if you needed the board to be just a little bit bigger, but like not you didn't feel comfortable in feeding just that little bit, what you could do is, you're reciprocating back and forth with this ID grinding wheel. You start reciprocating a little bit faster, and well, now you're building up a hydrodynamic layer on the ways. And the faster you go, the more of hydrodynamic lift you get. So it's lifting the part, ever so slightly up, which is increasing the engagement of the grinding wheel just, that little bit more. And if you can control that and how long you spark out for, and you can realistically achieve, you know, changes in dimension that are smaller than those 10 millionth graduations. But
That's nuts.
yeah,
That is so cool. Oshin Leahy was asking about the ASPE conference. He's considering going this year and wanted to know if you had any advice.
my advice would be go. I mean, I don't have a lot to compare it to, frankly, but as far as like, if you compare it to something like the ASME or any of the other engineering societies, it's a lot smaller. It's a lot more tight knit because, frankly, the field of precision engineering is just not as big. Um, so everyone knows each other. Everyone's very sort of friendly to each other and like collaborative because in this field, a lot of the motivation isn't there's not a crazy amount of competition. The motivation that everyone has is advancing, like just pushing the limits. Like how many decimal places can we get? Like by any means necessary. So it's there's a lot more collaboration than in other industries, I would say. So everyone we talked to there was super friendly and hey, like here's my email, like reach out if you need any help with anything. And it's a really good community to get involved with if you're into that sort of thing. It's a networking heaven, frankly. You can meet a lot of really, really neat people. Um, but yeah, definitely just if you can go, I'll see you there. We can meet up. We're planning on doing the student challenge this year, so I'll be there in a slightly more official capacity than I was last
Awesome.
year.
What's the challenge this year?
Oh, so this year, I'm really excited for this one. So it's an optical profilometry is the theme. And the challenge is basically using a Blu-ray optical pickup unit to do nanometer level profilometry on these freeform surfaces or whatever samples they give us.
Oh,
So,
that's cool.
I mean, a lot of people don't know this, but like the read heads inside like Blu-ray players and even like DVDs and CDs, they're like a marvel of frankly precision engineering. Because I mean, when you think about what they have to do, they have to look at this tiny little track that's written around a CD that's like maybe a micron or so wide, and there's pits, and then there's the normal surface, and then there's like pits in it, and this thing's spinning around. I think the speed's like the linear speed is something like 1.5 meters a second or something, and there's just thousands and thousands of little pits and valleys zooming by, and it's detecting these things by looking at the focus of a laser and saying, okay, well, servoing the focus of this laser to match whatever surface it's on. And you've got a little voice coil driving an objective lens that's got a bandwidth of some amount in kilohertz, and a 4 quadrant photo detector that can detect in what direction the laser's out of focus, with some really neat optics tricks that I've been geeking out on. All this is to say, they're very powerful devices, and the challenge is using those to take some very, very accurate measurements on these surfaces and make a really neat metrology tool, honestly. That, even after the challenge, I might just have to put one together for myself for personal use, because, I mean, you can, in theory, like the resolution of the height deviations you could measure, I mean, it's like in the single digit nanometers.
That's
Just with,
nuts.
yeah. And these things, you can buy them for like $10, these optical pickup units for Blu-rays. There's a few papers out there on the topic that I've looked at, and I don't know, super cool technology. It'll be a fun challenge.
Yeah, I mean, it sounds like you could build a incredibly quick profilometer out of one too. It's
Hmm.
like traditional ones are fairly slow too. So, if it's reading a meter per second, even if just sliding a part under it, it seems like it
Well,
could pick up.
the issue with using it for traditional profilometry is, and maybe profilometry isn't even the right word. That's what they're calling it, but the spot size of the laser, like it's focusing down to a point, but you can't focus it down to a point smaller than the wavelength of the light. So the optics in it are very good, and it's damn near diffraction limited. So the point is, like 450 nanometers, which is super close to the 405. That's the wavelength of the laser. Um, but you can't really have a higher spatial resolution than, a half a micron basically.
Right.
So you're not looking at macro surfaces, but you can't look at, like, you couldn't measure a a profile of, like, if you wanted to look at the, is this 1 micro-inch RA, or is it 10? You can't, you don't know, because the spot size of what you're looking at, it's relatively big. I mean,
Right.
half a micron's not not large in the grand scheme of things, but
But for what you're talking about, you're not
yeah,
going to be able to use this to measure the mirrors coming off of your lathe.
yeah, you can use it to measure the form accuracy of them across a range.
That could be cool, then.
But yeah, it's not a profilometer in the traditional sense.
Okay. Stan asked, "What would your dream job be in the industry?"
Hmm. Definitely. So I don't know exactly what field I'll end up in, although I know it'll be something to do with precision engineering. But I do know it'll be something with R&D, um, at a smaller company, because, as I was talking about before, I love the engineering, I love designing stuff, but I also want to be the guy to make it sometimes, because that's the other fun part. And frankly, like, your classic aerospace response be like, "Oh, I want to work at SpaceX or NASA." Well, you're not gonna get that at SpaceX or NASA. Like, you don't have the engineers designing the rocket parts, walking downstairs and machining the rocket parts.
Right.
That's not how that works. So it'll probably be, ideally, it's a smaller company where that sort of job is realistic. And R&D is the area in which you're going to probably see that. Just, whipping together prototypes or something real quick, um, doing engineering, but also, like, well, let's just try this real quick and see. We'll just throw something together and and make it work. But whatever it'll be, definitely precision engineering related, because I like the small numbers.
Ethan Patain asked, "Where'd you get the Matterhorn model?" He found his on GrabCAD and was curious where you found yours.
Oh yeah, the one for my Instagram. I think I got that off of a thingy. That actually is not a super great model. There's a weird artifact if you look in the video I posted of it. There's a weird, like, thing in the mesh. It's like a line or something that showed up in the final part. Um, yeah, I got it off Thingiverse. It was just a part to test out a new tool we got. That was the purpose of that thing. because we wanted to look. We had this cool new tapered end mill that said was good for surfacing or whatever. So we just tried to machine the Matterhorn to see how well that would work.
Awesome. Last question from the other half of the Precision Microcast. Adam asked, "Where will your next summer internship be?"
Ooh, well, I mean, nothing is set in stone yet. There's been some talking to some people. Um, I will say we've got eyes on the fancy red machines.
Okay.
That's
Okay.
some
Very cool.
that is I think the goal.
Awesome.
The fancy red machines,
Well,
or
that brings
whatever
us
color you want, because
right.
they'll make them in whatever color you want.
Yeah, very true. That brings us to shop news and new things. So, what's new in your world? I guess you're probably going back to school pretty soon.
Yeah, well, we do have some shop news and new things in back at school. Right before we left, we acquired a Mitsubishi EV 1400 EDM for the shop.
Congrats.
Um, Sort of puts us in the same situation as we were back when I started working at the Makerspace, where I have no EDM experience at all. We don't know how to run this thing, so we're gonna figure out how to run it. It was kind of a weird situation in which we ended up with it. It came from another department that ordered it, but then they couldn't use it or something. I don't know. So it just kind of like showed up one day. It wasn't like we were asking for one. It just kind of like, uh, the school needs a place to put this EDM. Do you guys want it? Um,
You're like, sure, of course.
Absolutely.
I'm not
So
familiar with that. Is that a wire or a sinker
it's a
EDM?
wire.
Sweet.
Yeah. A pretty decent size wire. I don't have again, I don't have any EDM experience, but I was looking at the specs on it, and I saw 50 nanometer programming resolution, and then that set off all sorts of alarms in my head. So that I'm sure we'll be making some cool stuff with that. All of the flexures, you know.
Yeah. Oh, yeah. That's really cool. That'll be a lot of fun this semester to dive
Hmm.
into, I'm sure.
Absolutely.
Do you guys have any licenses at the school of like a spree or something that could drive it?
Not currently. We've looked into some options for cam. There's a certain level of cam built into the machine. Like you can
Okay.
upload DXFs and whatnot directly to it, and that'll get you most of the way. I mean, I'm not going to attempt any crazy multi-axis lofting, right off the bat.
Right.
But I think for that you may need to use a cam system. But I mean, again, that's not going to be for a while. I think most parts are just going to be doing straight cuts, and DXFs are really all you need for that.
Okay. That's, yeah, a great place to start for sure. Well, that brings me to the last question I ask every guest every week, which is, what did you research this week? And it can be anything under the sun. Doesn't need to be machining related, but just what's been popping up in your browser.
Lasers.
Okay.
That has been the topic recently, and honestly, optics in general. It keeps being a sort of a sticking point that I'm running into in all of the work that I'm doing. Is like I'll get into something, and then there's optics involved, and I just don't have like the fundamental knowledge that I need to like understand. I want to get some more intuition as to how all that works, and specifically been reading Understanding Lasers by Hecht, or however you pronounce that. Um, just something that I've been interested in for a while and have been getting annoyed recently at my lack of knowledge in. So I'm just trying to dive in and tackle optics and lasers because I want to know how they work.
Awesome. Well, really cool. Thank you so much, Cyrus, for taking the time to come on the show and talk all about precision and
Yeah.
cool lathes and all that stuff. It's like insane the level that you guys work to and that you're learning to work to. I have never been near that kind of tolerance, and I don't think I have the skills to be anywhere near that kind of tolerance, but it's really cool to hear.
Yeah, absolutely. It was a blast to be on, and I hope I can continue to share what I learned from all this and help some other people get to these levels and help
Definitely.
myself get to these levels because Lord knows I'm nowhere close yet.
And then thank you to all the Patreon members. It helps me send people like Cyrus headsets so that we can have conversations like this and you can hear them. And thanks everyone for listening. I'll be back next week.